So we will be in your polar packet and all that fun stuff, and yeah. So week from today will be a test, okay? And that test will cover polars and complex numbers. And so that'll be next week, Thursday. Then, so basically, let me walk through the next today, so today and the next 11 days, so 12 total days. So today we're going to take some notes on some polars. Then tomorrow we're going to have some polars again, and then we're also going to give you the first of 3 final review packets. Your final for this class will cover all of trig, meaning it will go back to October. Okay? So it is a year-long final because it is the NTC final. Okay? So that's why you have 3 of these. You'll get 1 on Friday. Then we come back on the following Tuesday, and we're going to do some review of polars and some review of complex numbers. And then Wednesday, we'll do we'll study for your exam, and we'll give you the second review packet, and we'll make sure that everything's ready to go for complex numbers and polars test, which will be on Thursday. And that Thursday you will get review packet number 3. That leaves Friday the 12th as a review for the final, and then your final will be on May 16th and 17th. Okay, so we're going to give you, basically what's going to happen is we're going to give you the final on the 16th, and it needs to be completed by the end of your class on the 17th. So you have 6 total mods to take this one. And then Thursday, the 18th, we will do EMPT. We took the EMPT, remember, at the beginning of the year. We'll take it again on that day. And then we'll also go around and we'll talk to you about your NTC grades that day. And then on the 19th, we'll have an end of the year pre-calculus celebration. Okay? All right. So that is that. So let's get into it. Pitter patter. Okay. So this is a warm up. Off to the side, like you can do it at the bottom underneath those polar graphs or etc. Whatever you want to do there. OCD's kicking in here. You know, let's go right there and there and there. So I want you to find me the third roots. Okay. So find me the cubic roots of -2 plus 2i, and then I also want you to take -2 plus 2i to the third power. Go for it. Those 2. Now, the nice thing is we picked the same complex number, right? So we can put this complex number in trig form, and then we can use that for both of them after that. So if I put this complex number in trig form, so that would be -2 plus 2i in trig form. That is going to be, we'll call it z here, that's going to be 2 square roots of 2 cosine I sine of -135 degrees. Yes? Okay? So a couple of things just to remember to speed yourselves up. You got to look at what your complex number looks like. In this case, A and B were the same digit. And one was -2, one was +2, but they're the same digit of 2. So that's a 45, 45, 95. Okay? If one of them was a number and the other one was the square root of 3 times that number, then it's a 30, 60, 90 triangle. Okay? If it's something other than those 2, then you got to go through and you got to do all that trig calculation and all that stuff, inverse tangents and all that stuff. Okay? So there it is. So third roots. De Moivre says then that x sub 1, I'm just going to call it x sub 1 because that's kind of what the lingo that we've been calling it, is we are going to take the 2 square roots of 2 and we're going to third root that. and then we're going to take 1/3 times 135. Okay? So the third root of 2 square roots of 2, not very pretty. Okay? So what do we got actually? Calculator, there it is. 2 square roots of 2, that, and I want to take that to the 1/3 power. So I'm going to say that that is approximately just the square root of 2. Does that make sense? That's square root of 2. Yeah. So we'll call that the square root of 2. Because there's really 2 square roots of, there's 3 square roots of 2 in there. Okay, so that makes sense. CIS of 45 degrees. Agree with that for the first one. Okay. Second one, oops, that was the first one. Second one is going to be the square root of 2. Well, what's my angle?
15.
It is not 15. What do you got? 165. How did you come up with 165? Yep. So 360 divided by 3 is 120. Add 120 to 45. Yeah, add 120 to the next one. And if I were to add 120 to 285, I'd get 405. Subtract off 360, get it back down, go back to 45. So there's that one. If I'm evaluating it to the certain power, well, then that is going to be 2 square roots of 2 to the 3rd power, and then I'm going to take cosine I sine of 3 times 45. 2 square roots of 2 to the 3rd power is going to be 8/16 square roots of 2. Yes? Now, had you rounded, like the other day on the formative, they weren't pretty R values, so we took them rounded also. So like this would have been 1.1 or 1.41, and 16 square roots of 2 would be 22.63. Okay? Good stuff. Oh man, look at that. It's all kinds of goofy. Polar coordinates come in the form r comma theta, and we learned that yesterday. Okay? R is the radius, theta is the direction angle. So what I would like you to do now is I would like you to pick an angle and a radius. I don't care what angle you pick. I don't care if it's in degrees. I don't care if it's in radius. Okay? I want you to pick an angle and a radius. Plot that point. Okay, so this is number 7 now on your sheet. Okay? Plot that point. And then give me the 3 alternative names to that same point. Give you a couple minutes to do that one. Just a reminder that the 4 different versions of a point are positive, positive, so positive r, positive theta, positive r, negative theta, negative r, positive theta, and negative r, negative theta. Okay? Those are the 4 different versions. You can name any polar point. Do I have a volunteer to give me their original point? Oh, yeah. 290 degrees. Okay. All right. So if I were to plot that point, that would be right there. Agree with that? Okay. So the original point was 2, 90 degrees. Okay. One alternative, so that's positive, positive. Positive, negative would be 2, negative 270 degrees. Do we all agree with that? Okay. Negative R value now for the next two, which means in my brain I need to get to there because I need to get to that point in order to go negative back through the pole. Okay? So then that would be positive 270 degrees or negative 90. Agree? Okay. Good, good, good. Okay. So today, what we're going to do is, obviously I got to fix every single slide. Okay. We're going to change from polar to rectangular. Okay. So if we have, now it's going to be hard for you to see, but we're going to, in our brains, we're going to superimpose a polar graph right over the top of our Cartesian graph. Okay? So we're going to have this point right out here. In a Cartesian, okay, which is a rectangular, that point would be x, y. In a polar, it would be r, theta. So we need to come up with a way to flippity-floppity back and forth between them. Okay? So we know that this is a Batman and Robin right triangle. Okay? So this is x, this is y. We know that that's a right triangle, and we know that the hypotenuse is r. Okay? So if we needed to solve for r, we would just take the square root of x squared plus y squared. I've been doing that for a while. If we need to solve for theta, we would inverse tangent y over x. If we're in quadrant 1, we just do that. Drop your water bottle. Okay? If we're not in quadrant 1, then we're going to go theta prime, and we're going to drop any and all negative signs. Okay? You've been doing that now for the better part of 2 months. Okay? That should be normal for you. So that's how you go from rectangular into polar. Okay? The other way, if we're going to go polar into rectangular, well, I know based off of this triangle that the cosine of theta is equal to x over r, adjacent over hypotenuse. So total. I know that the sine of theta is y over r. So control. So I can solve those for x and y, And I can say that x equals r cosine of theta, and y equals r sine of theta. So those two methods that you've already seen them, because you've done plenty of SOHCAHTOA, are how we convert to and from that. Yep. I think that's a let's put it to work now. Bam. Change the point to the other form. Polar to rectangular or rectangular to polar. Exact answers if possible, meaning if it's on the unit circle, we want it in exact form. If it's not on the unit circle, then we're wrong. So we go back. Okay? So 3 square root of, or 3 comma pi over 2. Is that a polar point or is that a rectangular point? Polar. Why is it polar? Because it's an angle. Yep, exactly. It is an angle. Okay? So this is a polar point. So we need to go into rectangular. So x is going to equal r cosine of theta. Y is going to equal r sine of theta. Cosine at pi over 2. 0 times 3. 0 times 3. 0. So x is 0. Sine at pi over 2. Say louder, Ashley. 1 times 3. Okay? So my rectangular point is the point 0, comma 3. So if we look ahead to C, is this a polar or is this a rectangular? This is a rectangular one. So I need to go into polar. So my r is going to be the square root of 3 squared plus 1 squared, and I'm going to take the square root of that. Square root of 3 squared. Squared. Just 3, yep. 1 squared. 1, 3 plus 1, 4. Square root of 4. 2. Okay. Which quadrant is this rectangular point in? 1. Do I need reference angles? No, because I'm in quadrant 1. So I can go right to theta being the inverse tangent of 1 over the square root of 3. Where is, in quadrant 1, the tangent equal to 1 over the square root of 3? Degrees or radians, I don't care. It's on there. 30 degrees or pi over 6. So this polar point then would be 2, 30 degrees, or we would also accept 2, pi over 6. You now do B and D from that page. First one's polar to rectangular, correct? It's in polar, I've got an angle, I see a pi, I think of an angle. Okay? So then this is going to be x here equals r cosine of pi over 6. Y is going to equal r sine pi over 6. The cosine of pi over 6 is root 3 over 2. So this is 3 times square root of 3 over 2. So that's going to be 3 square roots of 3 all over 2. The sine at pi over 6 is 1/2. So that's going to be 3/2. So this rectangular point would be the point 3 square roots of 3 over 2, comma, 3/2. Yes? This one is a rectangular. We need to go to polar. So my r is going to be 2 squared plus negative 2 squared. That's going to be the square root of 8. So my r is going to be 2 square roots of 2. In terms of my theta, this is in quadrant 4. So this would be my theta prime, which would be 45 degrees because they're both the same. 2 divided by 2 is 1. The inverse tangent of 1 is 45 degrees. Quadrant 4 tells me then that my theta is 315 degrees, or what is that? 7 pi over 4. Yes? All right, let's do these bottom two here now, E and F. Rounding to 2 decimal places. So we've got -2, 5 pi over 8. Polar coordinate. I need to get it into rectangular. So I'm going to say x equals -2 times the cosine of 5 pi over 8. Now, what's the problem with 5 pi over 8? Not in the unit circle. And what else is the problem with it? Is it in degrees? No. So when I go to use this, what's this typically in? Degrees. What do I need to switch it to in order to do this problem? That's got to be in radians. The angle was given to in radians. Okay? DRG at the top if you're using the TI-30s. Okay? Switch yourselves over to radians. I get 0. It said round to 2 decimal places, 77. Actually, here, let's do this because I'm going to rewrite it anyways. I get 0.76537 over I get negative 1.84776. So those would be, so this point then would be in rectangular 0.77, comma, negative 1.85. Rectangular to polar when we round. So R here is going to be negative 3 squared plus negative 5 squared, square root thereof. That's going to be 9 plus 25. It's 34. We are not in quadrant number 1, so I'm going to reference angle. Now, here's the kicker. What's your calculator in? It's still in radians from the last problem, right? So if you want to get radians, I mean, you can keep it in radians, but if you want to go back to degrees, you got to switch your calculator back to degrees. Inverse tangent of 5 divided by 3 gets me 59.036 degrees. We are in quadrant 3. So that's going to be actual theta is 180 plus my reference angle. So here I would go square root of 34, comma, 239.04 degrees. You could also go 5.83. You could also go here. But I would put the little R symbol up there if you were to do it in radians. If you do it in radians, the angle that you find is 1.03037 radians plus pi then, because you're not using 180 degrees, you're using pi radians. So one of those. Okay. Good times. Easy graphs. Okay. So we also have to graph using our polar coordinates. Okay. What do you think a polar graph of r equals 2 looks like? Yeah. Circle with the radius 2, because we're looking at for all points that are 2 units away from the pole. Okay? So that's going to be a circle on the second ring. Looking for all points 2 units away from the pole. what would the graph for number 2 look like? Circle the radius of 3. But instead of like, if we were to actually draw it like this again, this is where the old school calculators were so much nicer. Okay, my old TI-82 was my old first ever graphing calculator, and it was awesome because it was, the processor was so slow, you could watch the circle being drawn as it was doing it. Okay? So this circle, instead of like, so on this one, I started here and I went around and came through that way. Here on this one, I'm going to go 1, 2, 3, but I'm actually starting here and going around this way. Would be the starting point for a circle with a radius of -3. Still gets a circle. Okay. Like it. There we go. What do you think a polar graph of theta equals 120 degrees is going to look like? Yeah.
Maybe just a line where everything will be
So a line that looks kind of like this. Mm-hmm. What about one that says negative 120 degrees for a theta value? Still a line? Yep, still a line. But now that way. Explain to me. I'm going to play dumb. It's not that hard for me to do. Explain to me why this is a line and not a ray. Meaning, we'll go back to the first one. Why is it a line and not just that? Because we have negative R values that would be in the same direction, just going the opposite way. Good job. Oh, that appears to be it. Look at that. So that is where we need to get to. Good times.